introduction into hyperbolic function. So I would start off with achieving the differentiation for sin inverse of x. Now foremost, to get the differentiation of sin inverse of x, we will have to just let y be equal to sin inverse of x. So I move the sin inverse to the left. This would give me sin y is equal to x. So now I would differentiate both sides with respect to x. So when I do that, this would give me differentiation of sin y is going to be cos y times differential of y, which is dy over dx. Differentiation of x is 1. So from here I can write dy over dx is 1 over cos y. Now you have to know the following formula. What is that? Cos squared y negative sin squared y is equal to 1. So cos squared y is equal to 1 positive sin squared y. So from here cos y is root of 1 positive sin squared y. Now dy over dx is equal to 1 over cos y. So therefore dy over dx is equal to 1 over, in place of cos y I'm going to write it as 1 positive sin squared y. But sin y is equal to x, so this is going to be 1 over root of 1 positive x squared. So this is my dy over dx. So what we have done here, we have obtained the differentiation for sin inverse of x. So the solution is going to be 1 over root of 1 positive x squared. So on the left hand side it's going to be differentiation of sin inverse of x. So this is a very important result. Now I'm going to show you that the same result is obtained using logarithmic function. So that was going to be our next question. I know that we are doing differentiation of hyperbolic functions, but I thought that I can bring this question to your attention. So we are expected to differentiate ln of x positive root of x squared positive 1. Now if I were to differentiate this would produce 1 over x positive root of x squared positive 1 times differentiation of x positive root of x squared positive 1, which can be rewritten as differential of x is 1, differentiation of root of x squared positive 1 is going to be 1 over 2 times x squared positive 1 raised to the power of negative half times differentiation of x squared, which is 2x. This is divided by x positive root of x squared positive 1. The 2 that we see can be cancelled, so we now have 1 positive x squared. So let me write that down, x over root of x squared positive 1, because the degree is negative half, right? So I can push it down. So this has to be divided by x positive root of x squared positive 1. Now if I were to take the LCM, I would get x squared positive 1 positive x divided by root of x squared positive 1. This is what I get from the numerator. Now I can bring this up, so that's going to be x positive root of x squared positive 1. Now clearly you can see that root of x squared positive 1 positive x and x positive root of x squared positive 1, these two can be cancelled. So this is equal to 1 over square root of x squared positive 1. What is this? This is nothing but differentiating ln of x positive root of x squared positive 1. This is what we got. Now why did I show you this? Because in the previous question we had to differentiate sin inverse of x and we got the same result, 1 over root of x squared positive 1. So that is why I want to show you how exactly these two results are correlated, even though one is produced by a logarithmic function and the other is produced by inverse hyperbolic function. before we could go further into differentiating inverse hyperbolic function, we will have to know a few things about hyperbolic differentiation. Now, sin x is given as e raised to the power of x negative e raised to the power of negative x divided by 2. This is sin. And cos x is given as e raised to the power of x positive e raised to the power of negative x divided by 2. So these two results are very vital, and it's very critical that we understand this first. Now, suppose you are asked to differentiate, say, sin of x, say d over dx of sin of x. This is asked. So this is nothing but d over dx of e raised to the power of x followed by negative e raised to the power of negative x divided by 2. Now I can rewrite this as 1 over 2 times, by linear property, this is going to be differentiating e raised to the power of x followed by differentiating e raised to the power of negative x. This is equal to 1 over 2 times. When I differentiate e raised to the power of x, remember, differentiation of e power x will give me e power x. That's critical. So this is going to give me e raised to the power of x followed by a negative sign. When I differentiate e raised to the power of negative x, I would get e raised to the power of negative x, but I would have to multiply it with the differential of negative x, which is negative 1. So this can be further rewritten as 1 over 2 times e raised to the power of x negative negative positive e raised to the power of negative x, which can be rewritten as e raised to the power of x positive e raised to the power of negative x divided by 2, which is nothing but Cautiox. So we have to remember, differentiation of sin x produces Cautiox. That's the first thing. So we will move on to see the differentiation of other hyperbolic functions. So now we got to obtain differentiation of Cautiox. Now this is nothing but d over dx of, I already told you, Cautiox is represented as e power x positive e raised to the power of negative x divided by 2. This can be rewritten as 1 over 2 times differentiation of e power x positive differentiation of e power negative x, which is nothing but 1 over 2 times. When you differentiate e raised to the power of x, you get e raised to the power of x. When you differentiate e raised to the power of negative x, you get e raised to the power of negative x. Of course, you have to multiply with the differentiation of negative x, which is negative 1. This can be rewritten as 1 over 2 times e raised to the power of x. Positive times negative is negative, so e raised to the power of negative x. This can be rewritten as 1 over 2 times e raised to the power of x. In fact, I can rewrite it like this: e raised to the power of x negative e raised to the power of negative x divided by 2. But what is this? This is nothing but sin x. So I can rewrite this as sin x. So what I've got on the left, I've got now differentiation of Cautiox is sin x. So this is a very important result. Now the question comes, what if someone were to give you, what is the differentiation? Question number 109. If someone were to ask you, how do you obtain the differentiation of hyperbolic tan x, what would you get? Now this can be rewritten as differentiation of sin x divided by Cautiox. Now I'm going to use UV method, right? So let me write that u over v method, quotient rule. That's nothing but v times u dash minus u times v dash divided by v squared. So if I were to use quotient rule, this is nothing but Cautiox times the differential of sin x negative sin x times the differential of Cautiox divided by Cautiox raised to the power of 2. This is equal to Cautiox, differential of sin x is Cautiox followed by negative sin x, differential of Cautiox is sin x divided by Cautiox whole square is cos squared x. Cautiox is cos squared x, negative sin x is sin squared x divided by cos squared x. Cos squared x negative sin squared x is 1 over cos squared x. 1 over cos squared x is nothing but hyperbolic secant squared x or sec squared x. So what have we got? We got differentiation of hyperbolic tan or tan x to be equal to secant squared x. So this is a very important result. Now you can also do the same thing. The same outcome will follow if you were to replace sin x by the formula e raised to the power of x negative e raised to the power of negative x over 2, and cos x is e raised to the power of x positive e raised to the power of negative x divided by 2. The same result will follow. So we will move on to see the other differentials of hyperbolic functions. Students, moving further, let us now study the differentiation of hyperbolic Cautiox. Now this is nothing but d over dx of Cautiox divided by sin x. Now once I get this quotient, I can apply quotient rule. D of u over v, which is nothing but v times u dash minus u times v dash divided by v squared. This can be applied. So this is equal to u over v. This is going to be sin x times differential of cos x negative cos x times differential of sin x divided by sin x raised to the power of 2, which is nothing but sin x differential of cos x is sin x followed by cos x times differential of sin x is cos x. So this is sin x raised to the power of 2. Now I can further rewrite it as sin x times sin x is sin squared x, cos x times cos x is cos squared x, sin x raised to the power of 2 is sin squared x. Now I've got sin squared x negative cos squared x, so I would like to rewrite this as cos squared x negative sin squared x. Now why am I doing this? Because I got a formula for this. Simple as that. What is the formula? The formula is 1 divided by sin squared x. But what do I have here? Negative. But what is 1 over sin? 1 over sin is cosecant, right? Hyperbolic cosecant. So this is going to be cosecant. Let me rewrite it like this: cosecant squared x with a negative sign, right? So it's hyperbolic cosecant squared x, or you can say it as, depending upon your pronunciation, if you can pronounce it as cosec squared x with a negative sign, it's fine. So what is this? This is nothing but differentiation of Cautiox. So it's a very important result. So what have we studied? Differential of Cautiox, hyperbolic cot, gives us negative cosecant or cosec squared x, or hyperbolic cosecant squared x with a negative sign. Now having got that, let us move on. So the next question 111, I would want to know the differentiation of hyperbolic secant x. Now this is equal to d over dx of 1 over cos x. I can use d of u over v, quotient rule, which is v times u dash minus u times v dash over v squared. This is the formula. By this formula, this is going to be cos x times differential of 1 negative 1 times differential of cos x divided by cos x raised to the power of 2. This is going to be 0. This is negative differential of cos x is sin x divided by cos x raised to the power of 2 would give me cos squared x. I can rewrite this as negative sin x divided by cos x times 1 over cos x. Negative sin x divided by cos x is in fact hyperbolic tan x with a negative sign, and 1 over cos x is secant x. So I can rewrite this as negative secant x tan x, hyperbolic tan x, or however you can pronounce it. So this is d over dx of secant x. So we got a lovely formula that we would have to use, or we would be using. So let us move on to 112. 112, we would want to know what is the differentiation of cosecant or hyperbolic cosecant x. So this is equal to d over dx of, I can write hyperbolic cosecant x as 1 over sin x, and I can use d of u over v, which is v times u dash minus u times v dash by v squared. This is a formula, quotient rule formula we would be using. So this is sin x times d of 1 negative 1 times d of sin x divided by sin x raised to the power of 2. This is 0. Differential of sin x will give me Cautiox divided by sin squared x. I can rewrite this as negative Cautiox over sin x times 1 over sin x. This is equal to cot x, or hyperbolic cot with a negative sign, times 1 over sin x is cosecant, hyperbolic cosecant x. So therefore d over dx of cosec x or hyperbolic cosecant x is equal to negative, you can write it as cot x cosecant x, hyperbolic cosecant x, or you can write it as negative cosec x cot x, all hyperbolic. Make sure to place the edge. So we got a beautiful formula. Now did you notice one thing? Both the components, or both the quantities secant and cosec, they both have a negative sign. So these are the major hyperbolic functions and their differentiations, and we will move on to see the inverse hyperbolic functions and their differentiations. Students, we are heading now to obtain the differentiation d over dx of cos inverse of x. Now we've already seen the differentiation of sin inverse of x, so we will now see and understand the differentiation of cos inverse of x. So I'm going to start by saying let y be equal to cos inverse of x. I'm moving this cos to the other side, cos inverse to the other side, so this would become cos x. In fact, this would become cos y. Cos y is equal to x. Now, so we got x is equal to cos y. Now I would be differentiating both sides with respect to x. So differential of cos y would give me sin. Differential of y is going to be dy over dx. Differential of x is going to be 1. So therefore, what I've got here, therefore I can write dy over dx to be as 1 over sin y. Now there is something we need to know. Cos squared y negative sin squared y, I given you this formula, is equal to 1. Therefore if I were to write sin squared y, I can state that cos squared y negative 1 is equal to sin squared y. So therefore our sin y is going to be root of cos squared y negative 1. I'm going to take this and I'm going to substitute it here. So this is equal to 1 over square root of cos squared y negative 1. But what is cos y? Cos y is x. So if I substitute here, what happens? So let me just write that down over here. So therefore dy over dx is equal to 1 over root of, in place of cos y I substitute x squared negative 1. So this is the final solution. So differentiation of cos inverse of x is 1 over root of x squared negative 1. But there is a condition. The condition is our x should be greater than 1. So make sure to place this condition. So that's a very important point. So having mentioned this, we'll move on to the next question. Now the next question is going to be, how are we going to obtain the differentiation of hyperbolic tan inverse of x. right? So this is a pertinent question. So for that, what I'm going to do is I'm going to take let y be equal to hyperbolic tan inverse of x. I'm moving this tan inverse to the left. I would get hyperbolic tan y is equal to x. Then I would be differentiating with respect to x both sides. Differential of hyperbolic tan y would give me secant squared y times the differential of y is dy over dx. Differential of x is 1. So therefore from your dy over dx is 1 over secant squared y. Now there is a formula. Now what is the formula? The formula is secant squared y is equal to 1 negative tan squared y. This is the formula we can use. So this is equal to 1 over 1 positive, or I should say 1 negative, right? 1 negative tan squared y. So this is what we have got. So from here we know that tan y, hyperbolic tan y is equal to x. So I can replace that. So that is equal to 1 over 1 negative x squared. So this is nothing but d over dx of hyperbolic tan inverse of x. Now a condition that this formula holds good is modulus of x less than 1. So that is critical. So this is the end of solution. I hope you can see that. That's 1 negative hyperbolic tan squared y. Now this is question number 115. Now in this question we would want to know what is the differentiation of hyperbolic cot inverse of x, and to get the solution what I'm going to do, let y be equal to cot inverse of x, and I would move this to the left, so that would give me cot y is equal to x. Next, differentiating with respect to x, this is going to give me negative differential of cot, hyperbolic cot is going to be negative cosec squared y, differential of y dy over dx, differentiation of x is 1. So having got this, from here we can get dy over dx is negative 1 over cosec squared y. So this is what we have got. Now we know that, so what do we know? We know that cosec squared y is equal to cot squared y negative 1. So this is equal to negative 1 over, I'm going to substitute this, hyperbolic cot squared y negative 1, but hyperbolic cot y is equal to x. So this is going to be negative 1 over x squared negative 1. So as always this is only valid for modulus of x greater than 1. So this is what we get when we differentiate hyperbolic cot inverse of x. So this is a very important result which we will have to remember. So having got this, we will move on to the next question. So the next question would be to find the differentiation of secant inverse of x. So for this I'm going to say let y be equal to secant inverse of x. I move this to the left side. I would get secant y is equal to x. I differentiate with reference to x. I get differential of secant x is in fact differential of secant y is secant y times tan y times differential of y is dy over dx is equal to 1. I can now rewrite dy over dx to be equal to 1 over secant y tan y, hyperbolic tan, right, with a negative sign. So far it's fine. Now what I want to do is I would like to get rid of this tan. So for that I'm going to use this formula. We know that 1 negative tan squared y is equal to secant squared y. So this is equal to negative 1 over secant y times tan. So what I can do, I will have to do some rearrangement in this case to get this tan. So I will push this to the left, so it's going to be 1 over secant squared y is equal to tan squared y. So therefore tan y, hyperbolic tan y, is equal to root of 1 negative secant squared y, right? So I will be using this over here. So that means I get a root of 1 negative secant squared y. This is what I get. But secant y is equal to x. So this is equal to 1 over x root of 1 negative x squared. Of course you have a negative sign. Now this is valid, okay, for values of x lying between 0 and 1. So what is this? This is d over dx of secant inverse of x. So this is a very important derivative. Okay, so I hope you have that in mind, and practice makes perfect. So we'll move on to the next question. So the final one when it comes to obtaining the differentiation of inverse hyperbolic function is cosecant inverse of x. So how are we going to do that? Foremost, I'm going to say let y be equal to cosecant inverse of x. I'm moving this. I would get cosec y is equal to x, and then I would differentiate with respect to x both sides. This would give me negative cosec y times cot y times dy over dx is equal to 1. So from here dy over dx is equal to 1 over negative cosec y times cot y. So this is what I've got. Now what I wish to do is I would like to replace cot. So let me write the formula down. Hyperbolic cot squared y negative 1 is equal to cosec squared y. So this is a formula which we would be using. So from here, if I were to write cot, hyperbolic cot squared y, this is going to be 1 positive cosec squared y, right? So I want to take this and substitute here. But before I could do that, this is cot squared y. So, but I want only cot y, hyperbolic cot, of course. So it's going to be negative 1 over cosec y. That's fine. And this is going to be square root of 1 positive cosec squared y. This is what I've got, right? So now I know that cosec y is equal to x, so this is going to be negative 1 over x root of 1 positive x squared. That's fine. So x cannot be equal to 0, so that's a condition. So this is going to be d over dx of cosec inverse of x. So this is a lovely differential. We have obtained the derivatives of all the hyperbolic function, which includes the inverse hyperbolic function also. So now it's time for us to set up the table. So I'm going to give you this table, and you can use this table as a guide and solve questions using that. So what I'm going to give you is an organized information of the derivative connecting hyperbolic function and inverse hyperbolic function along with their domain, so that it will be useful for you. So I will start off with writing the name of the function here with their derivative and the domain in which the function is alive. So foremost we will start off, okay, let me just have some blocks here so that we are on track. So having got that tabulated, let's start. So the function, the first one is shin or hyperbolic sine. So the derivative of shin is Cautiox, and the domain that it is valid is negative infinity less than x less than positive infinity. The next one is Cautiox. Derivative of Cautiox is shin x. I know you might be wondering why there isn't negative, because it is hyperbolic, and the domain is negative infinity less than x less than infinity. Now the next comes is hyperbolic tan. Differential of hyperbolic tan or tan x is secant squared x, and the domain is negative infinity x less than infinity. So after tan comes hyperbolic cot x. Differential of this is negative cosecant squared x, and x is not equal to 0. After this comes hyperbolic secant. The differentiation is negative secant x hyperbolic tan x, and the values for which it is alive is negative infinity less than x less than infinity. The next comes cosec x. Differential of this is going to be cosec x cot x, and x is not equal to 0. So the next after cosec is now inverse hyperbolic function. So this is going to be shin inverse of x. So differential of shin inverse of x is actually 1 over square root of x squared positive 1. So that is what we have achieved in the question that we performed in the earlier section. And the value for this is negative infinity less than, the domain is alive for values of x in this range. Now after this comes cos inverse of x, and the value for cos inverse of x, this is 1 over root of x squared positive 1. So this is going to be 1 over root of x squared negative 1, and for this x is greater than 1. Simple as that, because if x is not greater than 1, this one will perish. So after this comes tan inverse of x, and tan inverse of x is 1 over 1 negative x squared, very similar to our trigonometric tan inverse of x, which is 1 over 1 positive x squared. In this case it's negative, and the requirement is modulus of x for this is less than 1. If it is greater than 1, it will become negative, right? So we want this quantity to be modulus of x less than 1. So having obtained all this so far, let's complete the cot inverse of x, in fact hyperbolic cot, and that's going to be 1 over so you got a negative sign there, and it's x squared negative 1, and the domain, that's very important. that's going to be modulus of x greater than 1. Now we got two more quantities, which is secant inverse of x. Secant inverse of x is negative 1 over x times square root of 1 negative x squared, and the value is 0 less than x less than 1, and the final quantity is what is hyperbolic cosecant, right? So we will have to get that also. So that's going to be cosecant inverse of x, and let me write that down here. It's going to be 1 over x times root of x squared positive 1 or 1 positive x squared. Of course there is a negative sign here, and in this case if you are looking for the domain, x should not be equal to 0, right? Of course this is modulus of x, this should be positive x, so probably you can place a modulus sign there. So this is the list I would like to show you. So it starts with, okay, so I'm able to bring this all in one space. So function Shin inverse, differentiation of Shin inverse is cos inverse. The domain differentiation of cos inverse is Shin inverse, differentiation of tan inverse is secant squared, and so on and so forth. So make sure that it is written in your mind. So this is the last one. The last one corresponds to this quantity, negative 1 over x times square root of x squared positive 1 with x not equal to 0. So we will move on to do other questions, students. So we will now start off with our differentiation quest. We expected to differentiate d over dx of e raised to the power of x times Shin x. Now I'm going to, you can either use UV method directly, but it is okay. What I'm going to do is I'm going to rewrite this Shin x as e raised to the power of x negative e raised to the power of negative x divided by 2. So with this I can rewrite this as 1 over 2 times d over dx of, now e raised to the power of x times e raised to the power of x, that's going to be e raised to the power of 2x followed by a negative sign, and e raised to the power of x times e raised to the power of negative x, that's e raised to the power of 0, which is 1. So if I were to differentiate this, I would be getting 1 over 2 times differential of e raised to the power of 2x is e raised to the power of 2x times 2. Differential of 1 is going to give me 0. Of course there is a negative sign, we don't have to be worried about that. So 2 and 2 gets cancelled, giving me e raised to the power of 2x. So this is what we have got. Now I'm going to show you the same question by using product rule. So this is question number 118 and question number 119. The same question I'm going to use product rule. So we know that d of u times v is u times v dash positive v times u dash. So this is going to be e raised to the power of x. Differential of Shin x will give me cos x positive Shin x. Differential of e power x is going to be e power x. Now we got something like this. I'm going to take e power x out. So this is cos x positive Shin x. So this can be rewritten as cos x is e raised to the power of x positive e raised to the power of negative x divided by 2. Shin x is e raised to the power of x negative e raised to the power of negative x divided by 2. I can rewrite this as e raised to the power of x. 2 is common, we can take that out. So you get e raised to the power of x plus e raised to the power of negative x plus e raised to the power of x negative e raised to the power of negative x. E raised to the power of x with a negative sign, of course, can be cancelled. So you get e raised to the power of x and e raised to the power of x. So you can add these two together. So you get 2 times e raised to the power of x. 2 can be cancelled. So you get e raised to the power of x multiplied with e raised to the power of x, which is nothing but e raised to the power of 2x. So you get the same component over here and you get the same component over here. The only difference between these two is that the number of steps that got involved. So if you're going to write an algorithm to handle situations like this, you will have to always approach this solution from the least number of steps utilized. So have that in mind. Now let's do another question, question number 120. I would like to show you what happens if we differentiate hyperbolic secant of 1 over x squared. Now we know that I've just showed you that differentiation of secant x is equal to negative secant x times hyperbolic tan x. So we know this. So if I were to use this formula, this is going to be negative secant x, that's going to be 1 over x squared, times tan, hyperbolic tan, that's going to be 1 over x squared, times differentiation of 1 over x squared. So how do we get the differentiation of 1 over x squared? This is nothing but d of x power minus 2, which is nothing but negative 2 times x raised to the power of negative 2 negative 1, which is negative 2 x raised to the power of negative 3, which can be rewritten as negative 2 over x to the power of 3, right? So whenever you have a quantity like this, the best way is to take it to the numerator and then you differentiate, because I am basically using this formula, d of x power n is equal to n times x raised to the power of n negative 1. So by this formula, this is negative 2 times x raised to the power of negative 2 negative 1, which gives me negative 3, and this is a negative exponent, so it can be brought down, and that's the reason I'm bringing it down, retaining the negative sign. So if I were to rewrite this, this is going to be negative secant of 1 over x squared times tan of 1 over x squared times negative 2 times x to the power of 3. So when you want to write this, this is positive 2 times over x to the power of 3 secant of 1 over x squared times tan of 1 over x squared. So this is the final solution for our question. So question number 121, d over dx of shin of ln x. Now we already know that if I were to differentiate sin x would give me Cautiox. So we have already studied this. So this is going to give me cos of ln x times differentiation of ln x, which is equal to cos of ln x times differential of ln x is 1 over x. So if I want to rewrite this, I can rewrite this as 1 over x times cos of ln x. So this is my solution to the question. Now if in case you're not happy with this, then you can still reduce it by using the Cautiox formula, which is e raised to the power of x positive e raised to the power of negative x over 2. So what I wish to do is I would like to substitute this outcome. So this is going to be 1 over x times e raised to the power of ln x positive e raised to the power of negative ln x divided by 2, which is equal to, so I would rewrite this as 1 over x of e raised to the power of ln x positive. Now there is a negative sign here, right? So I'm going to take it to the exponent of x. So that's going to be e raised to the power of ln of x raised to the power of negative 1. Now the reason I did that, clearly we know that e and ln, they get neutralized, right? So I will get an x here. If I were to do the same thing, then this will become negative x. So both of them will get cancelled and we will get an output of 0, but that isn't the right answer. That is ambiguity. So that's the reason I'm just taking the exponent first to the, in fact the value of negative 1 as an exponent of x. So this is rewritten as 1 over, of course I can write this as 2x. Now e and ln, they get neutralized, giving me x. and e and ln they get neutralized, giving me x raised to the power of negative 1. So this can be rewritten as 1 over 2x of x positive 1 over x. Now this is equal to, if I were to take the LCM as x, this is going to be x squared positive 1 times 1 over 2x. So x and x can be multiplied, so I get x squared positive 1 divided by 2 times x squared. So this is what I get when I differentiated shin of ln x. Now we can actually verify if this result is true. It is possible. So how is it possible? Now let me just use the space here. So I want to use the space here. Now we have got this right. We are expected to find the differentiation of shin of ln x. This is the expected one. But we know that shin x is e raised to the power of x, negative e raised to the power of negative x over 2. We know this. So this is equal to d over dx of e raised to the power of ln x negative e raised to the power of negative ln x divided by 2. Now I can take the 1 over 2 out and write this as d over dx of e raised to the power of ln x negative. Now I know that e and ln get cancelled, so you will have negative x coming down, but I don't want to do it like that. As I mentioned to you, I want to push this as an exponent, so that would mean I would have e raised to the power of ln x power negative 1, right? So now it's safe to neutralize e and ln. So that's going to be 1 over 2 d over dx of x negative x to the power negative 1, right? So this is equal to 1 over 2 times d over dx of x negative 1 over x. This is what I've got. Now if I were to differentiate this, differential of x would give me 1, followed by differentiation of this is going to be negative 1 over x squared, right? Differentiation of 1 over x. So I can rewrite this as 1 over 2 times 1 negative negative positive 1 over x squared. So if I were to take the LCM as x squared, this is going to give me x squared positive 1, which is nothing but x squared positive 1 divided by 2 times x squared, right? So clearly you can see how we have got the same solution in both the ways. So this is a beautiful problem, and I've shown you 2 different techniques by which this problem can be applied. So this is 121, and probably I can put this as 122 just to have a differentiation. So we'll move on to the next question. Okay students, I want to utilize this space here, 123. So we expected to differentiate d over dx of, we actually did sine or shin of ln x, right? So now what I will do is I want to know what is ln of shin x. So differentiating this would give me 1 over shin x times differential of shin x. Differential of shin x is Cautiox. I already have a shin x here, so this is going to be hyperbolic cortex. So this is the solution for the question. So I will draw the red line. So we'll move on to the next question. Students, question number 124. Let us try to obtain the differentiation of Cautiox divided by 1 positive shin x. Now I would be using u over v form, which is nothing but v times u dash minus u times v dash divided by v squared. So by this is equal to 1 positive shin x. Differential of Cautiox is going to be shin x negative Cautiox times differential of 1 positive sin x would give me Cautiox, divided by 1 positive sin x raised to the power of 2. Now this is equal to sin x times 1 will give me sin x times sin x will give me sin squared x, Cautiox times Cautiox will give me cos squared x, divided by 1 positive sin x raised to the power of 2. But we know that cos squared x negative sin squared x is equal to 1. So I'm going to rewrite this as sin x positive. In fact, if I were to take a negative sign out, so let me write that like this, negative sign out, this is going to be cos squared x negative sin squared x, right? Negative times cos squared x will give me negative cos squared x, negative times negative sin squared x will give me positive sin squared x, divided by 1 positive sin x raised to the power of 2. So this is going to be 1, so this is going to be sin x, it's 1 here, so there is a negative sign, so I need to cater to that, so I place a negative sign there. Now I got a 1 positive sin x raised to the power of 2. Can I do something about it? Of course I would not be able to do anything. I will have to just stop there. 1 positive sin x whole square. That's the best we can do in this case. Probably I don't think we can reduce it any further. So this is a good place to draw our red line as far as this question is concerned. Now question number 125. Just in case if this question is reversed, instead of Cautiox over 1 positive sin x, if you have got say sin x over 1 positive Cautiox, then the solution would be totally different. So I'm going to apply u over v formula. So with that, this is going to be 1 positive Cautiox times differential of sin x, that is Cautiox negative sin x, times differential of 1 is 0, differential of Cautiox will give me sin x, divided by 1 positive Cautiox raised to the power of 2. Cautiox times 1 is Cautiox, Cautiox times Cautiox is going to be cos squared x, sin x times sin x will give me sin squared x, divided by 1 positive Cautiox raised to the power of 2. Now this is cos x positive, cos squared x negative sin squared x. I told you we have already seen it. It's 1. This is followed by 1 positive Cautiox raised to the power of 2. Now clearly Cautiox positive 1, 1 positive Cautiox. This can be cancelled, right? So this is going to be 1 over 1 positive Cautiox. So clearly you can see how different, just because the problem gets changed, the solution also gets changed, and this solution looks more appearable, right? So we'll move on to the next question, students. Students, we are expected to differentiate hyperbolic tan inverse of sin x. Now foremost, it is imperative that we know what is the differentiation of hyperbolic tan inverse. So before that, let me just specify what it is. So we have already found out that hyperbolic tan inverse of x to be as 1 over 1 negative x squared. Now just along the lines, it is imperative to know that differentiation of tan x is 1 over 1 positive x squared. So this is 1 positive x squared, this is 1 over 1 negative x squared. So there is a sign change for differentiation of hyperbolic tan inverse of x. So having got that out of the way, let us apply the differentiation. So this is going to give us 1 over 1 negative, the x term here is sin x. So it's going to be sin x raised to the power of 2 times differentiation of sin x. So this is going to give us differentiation of sin x is going to be cos x. So 1 negative sin x raised to the power of 2 is going to be 1 negative sin squared x. Now we know that 1 negative sin squared x is cos squared x. So that's exactly what I'm placing here. and in the numerator we got cos x. So clearly a cos x and a cos can be cancelled, giving me 1 over cos x. But 1 over cos x is secant x. So therefore we have a differentiation in this fashion. So differentiation of tan inverse of sine of x is secant x. Students, we are expected to obtain the differentiation of x squared times tan inverse of x positive 1 over 3 times ln of 1 negative x raised to the power of 3. So I'm going to rewrite this as d over dx of x squared times hyperbolic tan inverse of x positive 1 over 3 times of d over dx of ln of 1 negative x to the power of 3. Now this can be further rewritten. In fact, I'm going to apply the product rule. So d of u times v is equal to u times v dash positive v times u dash. This is the formula for product rule. So if I were to apply the product rule formula here, I'm going to get x squared times differentiation of tan inverse of x. So hyperbolic tan inverse of x is equal to 1 over 1 negative x squared, which we already know. So this is the formula I'm applying, right? So positive tan inverse of x times differentiation of x squared, that's going to give me 2 times x. Positive 1 over 3 times differentiation of ln of 1 negative x cubed, that's going to be 1 over 1 negative x cubed times differentiation of 1 negative x cubed, that's going to be negative 3 times x squared. So this can be further rewritten as x squared divided by 1 negative x squared positive 2x times tan inverse of x. A 3 and a 3 can be cancelled. You got a negative and a positive, so that's going to be negative there. So x squared divided by 1 negative x to the power of 3. So this is the outcome we have got. If the denominator were to be 1 negative x squared, then we can apply some simplification. So, but it isn't not so. So we have to be contented with this. But instead of this, if we were to be given a question like this, say 129, we are expected to differentiate x times tan inverse of x positive 1 over 2 times ln of root of 1 negative x squared. Well, there isn't a root here, so let me just, okay, I have just taken a root. I don't want to change the question, so let us assume that there is a root. Okay, so let me just continue with this. Now this is equal to, I'm going to rewrite this as d over dx of x times hyperbolic tan inverse of x positive. I can take this 1 over 2 out and then differentiate ln of, this is actually 1 negative x squared raised to the power of 1 over 2, right? So this is what I've got. Now before I could apply the differentiation for this, I would like to probably, let's just continue. So this is going to be UV form. So if we were to apply UV form, this is going to be x times differentiation of hyperbolic tan inverse of x is 1 negative x squared positive tan inverse of x, tan inverse of x, hyperbolic tan inverse of x times differential of x is 1 positive 1 over 2 times. Now this is actually 1 over, if you want you could have, you can actually bring this 1 over 2 in the forefront. So what I'm just trying to show you here is this can be rewritten as 1 over 2 times d over dx of 1 over 2 times ln of 1 negative x squared. So we can do that. How are we able to do that? Because of the fact that ln a raised to the power of b is b times ln a. So by that we can have the quantity re-written like this. If you are not happy, you can simply differentiate it the way you want it. So there isn't any harm in that. But still you will be able to achieve the results. Okay. But since I've already converted ln of 1 negative x squared raised to the power of half as half times ln of x squared, I will use this. So performing the differential operator on this is going to give me 1 over 2 is a constant. So I differentiate ln of 1 negative x squared. That's going to be 1 over 1 negative x squared times differentiation of 1 negative x squared. That's going to be negative 2 times x. So this is what I have got here. Of course, I can cancel the 2's that are present here. So I'm going to rewrite this. So this is equal to x divided by 1 negative x squared positive hyperbolic tan inverse of x positive. In fact, I could have rewritten this as negative x, because negative times positive should have been negative. But anyway, I will do it in the coming steps. So I got a 2 here, so it's going to be 2 times 1 negative x squared. So this is what we have got. Now what I can do is I can actually club these two together. Okay, so if I were to club these two together, I can take x over 1 negative x squared out. If I were to do that, I get a 1 here, and then this is 1 over 2 positive hyperbolic tan inverse of x. So this is going to be 1 followed by in fact it's 1 negative 1 over 2. That's going to give me 1 over 2. So I can rewrite this as x over 2 times of 1 negative x squared positive tan inverse of x. So this is the solution and a good place to draw the red line. Students, we have given this question. We are expected to obtain the differentiation of hyperbolic cot inverse of secant x. Now before we could proceed, we would like to know what is the differentiation of hyperbolic cot inverse of x, which is negative 1 over x squared negative 1. So we will use this over here. So this would be rewritten as 1, of course with a negative sign, divided by secant squared x negative 1. So this is what we have got. Of course we need to differentiate secant x. Now differential of secant x is secant x times tan x with a negative sign divided by, now we have a formula, secant squared x negative tan squared x is equal to 1. So from here secant squared x negative 1 is equal to tan squared x. So if I were to use this is going to be tan squared x. So clearly a tan and a tan can be cancelled, giving me negative secant x divided by tan x. Now secant x is 1 over cos x, tan x is sin x over cos x. I can flip this and rewrite this as cos x over sin x. I can cancel cos x cos x. This is going to give me negative 1 over sin x. But negative 1 over sin x is cosecant x with a negative sign. So we have got a beautiful differentiation, which is cot inverse of secant x has produced to me this outcome. Now moving on, question number 131. If we were asked to obtain the differentiation of, say, sin inverse of tan x, what we will do? Now we will have to use this formula, right? So d over dx of sin inverse of x is equal to 1 over root of 1 positive x squared. So this is a formula we will have to use. And sometimes this form, we can also rewrite this formula in this fashion, okay, root of x squared positive 1. So it doesn't matter, either you write it as 1 over root of 1 positive x squared or 1 over root of x squared positive 1. So by that formula, this is going to be 1 over root of tan x raised to the power of 2 positive 1 times differentiation of tan x. Differentiation of tan x will give me secant squared x divided by root of, now this is actually tan squared x positive 1. Now we know that secant squared x negative tan squared x is equal to 1. So you move that, so you get secant squared x is equal to 1 positive tan squared x. So in place of 1 positive tan squared x or tan squared x positive 1, I will replace secant squared x. So this is equal to secant squared x divided by root of secant squared x, which is equal to secant squared x divided by root of secant squared x is secant x. I can cancel it, giving me secant x. So this is a good place to draw the red line. So we are expected to obtain the differentiation of cos inverse of Cautiox. Now foremost, we will have to recollect what is cos inverse of x derivative. So when we differentiate, we got 1 over root of x squared negative 1. So this is for cos inverse of x. Now remember that differentiation of sine inverse or shin inverse of x is 1 over root of 1 positive x squared. In this case, it is x squared negative 1. So if you don't want to write it as 1 positive x squared, if you were to write it as 1 over root of x squared positive 1, clearly you can identify the formula of shin inverse of x with cos inverse of x, because derivative of shin inverse of x is 1 over root of x squared positive 1, derivative of cos inverse of x is 1 over root of x squared negative 1. So applying this derivative formula into this question, this is going to be 1 over square root of, instead of x I got cos, so cos x raised to the power of 2 negative 1 times differentiation of cos x. Now differentiation of cos x will give me shin x divided by root of cos squared x negative 1. But we know that cos squared x negative shin squared x is equal to 1. So that means cos squared x negative 1 is equal to shin squared x. So this is going to be rewritten as shin x divided by root of shin squared x, which is nothing but shin x over root of shin squared x will give me shin x. So clearly shin x can be cancelled, giving me 1. So which is the acceptable result. So now we know that cos inverse of cos x is actually x, differentiation of x leads us to 1. So that is a good result. So having obtained the result, let's go on to the next question. So question number 133. We are expected to differentiate, say, sine inverse of hyperbolic tan x. Now it is imperative to know that differentiation of sine inverse of x is equal to 1 over root of 1 negative x squared. This is the formula for sine inverse of x. So using this formula, this is going to be 1 over root of 1 minus tan x raised to the power of 2. I'm going to rewrite this as 1 over root of 1 negative hyperbolic tan squared x. But 1 negative hyperbolic tan squared x is nothing but, of course, we have to differentiate this. So differential of tan x has to be present here. So differential of tan x is going to be secant squared x. So I will place that secant squared x over here. So coming back to the point, this is secant squared x and root of, so before we could go to the root of, let's look into 1 negative tan squared x or hyperbolic tan squared x. So what is that? That is nothing but secant squared x. because of the formula. So this can be rewritten as secant squared x divided by root of hyperbolic secant squared x will give you hyperbolic secant x. Secant x and secant can be cancelled, giving me secant x. So this is a good place to draw the red line for this particular question. So this is 133. We will go on to the next question. So let's do question number 134. I will be using this space that is present here. We expected to find d over dx of hyperbolic tan inverse of x divided by 1 minus x squared. Now before we could do this, it is imperative to know that hyperbolic tan inverse of x is 1 over 1 negative x squared. So we will be using this result. Now the formula we would like to employ here, so let me write that down. D of u over v is equal to v times u dash minus u times v dash divided by v squared. This is the formula that we will have to use. So by using that formula, what I'm going to do is I'm going to differentiate this. So let me start off with the equal to sign. So this is equal to 1 negative x squared times differentiation of hyperbolic tan inverse of x. That's going to give me 1 over 1 negative x squared followed by a negative sign and tan inverse of x times differential of 1 negative x squared. That's going to be negative 2x divided by 1 negative x squared raised to the power of 2. Now clearly 1 negative x squared, 1 negative x squared can be cancelled, giving me 1 followed by negative negative positive. That's going to be 2 times x hyperbolic tan inverse of x divided by 1 negative x squared raised to the power of 2. So this is what I've got.